In this video, we're going to look at the standard deviation. This is from section 2.7 in your OpenStax statistics book. It would be notated by these symbols here, a lowercase sigma or an S. This is for the population, is a sigma, and S is for the sample. So standard deviation is a measure of variation based on how far each data value deviates or is different from the mean. It's always positive. It's 0 if all the data values are equal. It'll get larger as the data spreads out. So if you imagine like data squished together versus uniform versus really spread out. It has the same units as the original data. It can be highly influenced by outliers, similarly like the mean. It is interpreted as the average is the mean, give or take the standard deviation. So the variance is just the standard deviation squared. So we'll look at some examples and some graphs of this. Another measure of spread is the range. That just gives you the difference between the highest and lowest, so like how far apart the data is in general. So here's a sample of peanut butter jar prices. It's example 2.24. This maybe is old prices or small jars, probably much higher now. Be sure to interpret your answer in context of the problem. So you should have the units matching and add some sentences or interpretation if you need to as applicable. So the first thing to do would be to identify the highest and the lowest values. So it looks like we have a $3.99 jar and $3.29. So go ahead and subtract those and jot down the answer. Okay, so the range is 70 cents. It would be a lot different if we had one that was really high, like $10, and we had this really big range from the low to the high. But these are pretty close together. Let's look at standard deviation. To find the standard deviation and variance, we're going to use technology and interpret the standard deviation in context of the scenario. So these are our prices without the dollar symbol so that you can copy and paste into Stapplet. So go ahead and pause the video and do that now, or type them into Stapplet. And then look at your summary statistics. And I'm going to go ahead and reveal what the answers are now. So the standard deviation came out to be 0.261 or 26 cents. The variance is that same number squared, or 68 cents. When we want to compare values from different data sets, we need to kind of boil it all down to, instead of apples and oranges, we have apples and apples. So the standard deviation is useful when comparing data values that come from different data sets. If the data sets have different means and standard deviations, then comparing the data values directly can be misleading. So we want to look at the number of standard deviations away from its mean value. So we're going to use this formula that we would use the value minus the mean divided by the standard deviation. In this example, a student, Pat, was taking done taking midterms. She received a grade of 82 on her statistics exam, where the mean grade was 74 and the standard deviation was 12. She received a grade of 72 on her biology exam, where the mean grade was 65 and the standard deviation was 10. Lastly, she received a grade of 91 on her kayaking exam, that must be fun, where the mean grade was 88 and the standard deviation was 6. In what class did Pat relatively score better? So, 91, you think, oh, that's the highest, but how does that compare like difficulty level relative to the class, So let's take a look. We can figure that out by figuring out the number of standard deviations for each of those. So we're going to call this a z-score is what we call this. So the formula is z equals x, which is our variable value, minus x bar, which is our mean. So you do that operation first, then divide by s. So standard deviations are always positive, but the z-scores could be negative or positive. So it could be above or below. So if we fill that in, you can go ahead and start with the first one for the statistics z-score. She had an 82 minus 74 was what the mean was. So we're going to see the difference from the mean. But now we're going to divide by the standard deviation to give us a good picture, to get it all instead of apples and oranges to apples and apples. Okay, so when we divide that out, we get 0.666, so on and so forth, and we round to the nearest hundredth. So z equals 0.67. Z-scores do not have units like standard deviation does. So this is 0.67 above the mean, the number of standard deviations above the mean. So to figure out and compare, we want to find the z-scores for the biology exam. So go back up here to this part, the second sentence here. She received a grade of 72 on her biology exam. The mean was 65, standard deviation 10. So plug that into this z-score formula and find z. To go ahead and do that now, as well as for the kayaking exam. And then we'll look at how they relate to one another and compare. So pause the video and write that out now. Okay, I'm going to reveal the answers now. So the biology z-score was 0.70 and the kayaking score was 0.50. So if we look back at what our statistics was 0.67 and biology 0.7. So the biology was the one where she scored relatively better on. So the answer for that would be biology, and here's showing why. Okay, now on to the next problem. We have z-scores again, just more clearly written out. Z equals x minus x bar, or the mean, all divided by s, the standard deviation. Two swimmers, Angie and Beth, from different teams wanted to find out who had the fastest time for the 50-meter freestyle when compared to her team. Which swimmer had the fastest time when compared to her team? So use the z-score formula, plug in the data given in the table. We have Angie had a time of 26.2. The mean time was 27.2. Standard deviation 0.8. Beth 27.3. Team mean time was 30.1. Standard deviation 1.4 for that one, so a lot bigger there. So pause the video and take a moment to work out the details on that. Okay, and I'm going to reveal the answer now. Angie's score, you can see the computations there, equals negative 1.25. So she was that far below the mean. Beth was -2 below the mean. So it looks like Angie had the faster time relative to her team. Here is another example or work along. We have example 2.32. In a 5th grade class, the teacher was interested in the average age and the sample standard deviation of the ages of the students. The following data are the ages for a sample of n equals 20 5th grade students. The ages are rounded to the nearest half year. So there's the data set laid out there in order. You're going to want to use Staplet. We do not use the formula method as shown in your book, or you might see like maybe ChatGPT has you do that, or just some other solution generators that give you this big formula to work out, or videos you might find. Really just copy and paste and put it right into Staplet and look at your statistics summary and find those values. And we've done that several times already, so I'm not going to go through the whole process again. Pause the video and jot down those numbers, the mean and standard deviation. Okay, so I'm going to reveal the answer in a moment. And we'll be using this formula now. It's just a derivation of what we just had. When we want to find the variable, we take the mean plus the number of standard deviations times the standard deviation itself, or Z we could write instead of number of standard deviations there. So for the first part, we have the mean is 10.525, round to 10.53. Standard deviation is 0.716, round to 0.72. Remember, standard deviation has units, so does mean, but z-scores do not. So now let's try plugging into this formula up here. And we're going to find the value that is 1 standard deviation above the mean. So we have this information and we want to find out, like, what would an actual x value be that's 1 standard deviation above the mean. So we plug in our value, our 10.53 plus 1 for the z-score, or number of standard deviations, times 0.72, our standard deviation. And we would get 11.25. Be sure to follow order of operations. Do your multiplication first, then your addition. Now we're going to look at finding a value that is 2 standard deviations below the mean. So this time we want to put our z in as -2. So this time we're plugging in the z that we're choosing, or that's dictated by the problem, and finding a data value. So go ahead and try that. Plug it into the formula. You can pause the video. Okay, I'm going to reveal the answer. 10.53 minus 2 times 0.72. And I get 9.09 years. Now find the values that are 1.5 standard deviations from the mean. Above and below is what we want on that one. So pause the video and go ahead and try that on your own. And I'm going to go ahead and reveal the answer. Okay, so the answers are 9.5 years and 11.61 years. So this is going to be a useful tool a little later when we're doing dealing with more data sets and have questions that we need to know about, and those above and below and comparisons. So you'll be having some problems related to that. Now we're going to look at the next slide. Just to wrap this up, and it leads into something you'll see a little bit later. There's just a concept here. We have something called Chebyshev's rule. The following list gives you a few facts that provide a little more insight into what standard deviation tells us about the distribution of the data for any data set, no matter what the distribution of the data set is. So it could be skewed or not. At least 75% of the data is within 2 standard deviations of the mean. 89% is within 3. 95% is within 4.5 standard deviations of the mean. That's known as Chebyshev's rule. So here's just a picture of what that would look like. So even though this is not a normal distribution or symmetrical or anything, you can still see where the brunt of the data is going to be in the 75% in the middle there. The empirical rule is even better, and we could work with that a lot and do a lot of things with that. But there are great technology pieces we can use now, programs, and that help us out getting very specific values. So we'll jump into this later when we talk about normal distribution and how they compare. The following list is about the empirical rule. So if you have a bell-shaped or symmetric distribution, 68% is within 1 standard deviation, 95% is within 2, and 99% is within 3. Again, that's the empirical rule. And that's what this looks like. So we could figure out values this way. But like I said, there's going to be some really nice technology and programs we can use to help us with that instead. All right, so that is it for Chapter 2. Have a great day. Thank you for watching.